Hello guys, welcome back to another video on my channel. This is going to be a relatively shorter video, but that's fine because this question is one of my favorite questions in the recent times that I've encountered. So let's get started. We have I, the integral from 0 to pi, 0 to 2 pi. So you might notice there was a theme with the double integrals in the past few videos. Sine y, e to the sine y, and then all this is in the exponent, cosine of x minus sine of x dx dy. Okay, well, we can do one thing before proceeding forward. That's simplifying the exponential, the factor in that exponential with the cosine and the sine. We can simplify that. We can use the following identity. We can see that cos of x plus pi over 4 using the compound angle formula is cosine x cosine pi over 4 minus sine x sine of pi over 4. So cosine pi over 4 and sine pi over 4 are both equal to 1 over the square root of 2. So that gives us 1 over square root of 2, which can be factored, times cosine x minus sine x, the entire quantity. Okay, and that is more or less like the factor we have in the exponential, the cosine x minus sine x, except we have this annoying root 2 factor. So let's multiply with the root 2 on both sides. So root 2 cosine x plus pi over 4 gives us what we want, cosine x minus sine x. So we can replace that entire thing in the exponential using this left hand side we have here. So square root 2 cosine x plus pi over 4. And when I do that, I will get, and I can also interchange the order of the integration because they're both independent of each other in the bounds. So we have integral 0 to 2 pi, integral 0 to pi sine y e to the sine of y and square root 2 cosine of x plus pi over 4 dy dx. Now here comes the next great insight, and this insight escaped me because I wasn't careful the first time I was trying to solve this. That is, if you look at the range in x, so x goes from 0 to 2 pi, and the way x is defined, it's an angle, and with angles we have that x is the same as x plus 2 pi. So after 2 pi we just go back to the starting point, which is at 0. That's why when we write this interval, we have to include 0 once and then therefore exclude 2 pi because we've included 2 pi. 2 pi is the same as 0 the same time. So with that, what we can do is we can force this coordinate change. So we can say let x plus pi over 4 go to x. You might say, well, that's fine, but we have to account for the bounds. I'm telling you, you don't, because when you do that, our range in x is 0 to 2 pi. It's the entire angle range, unlike y, where it's just 0 to pi. So in the x range, from 0 to 2 pi, we shifted by pi over 4, using this this property that x is identified with x plus 2 pi, we will see that this doesn't really affect the bounds because the bound was the entire angular range. Shifting the angle by pi over 4 or minus pi over 4, some arbitrary angle, doesn't impact that, just because x is identified with x plus 2 pi, or any integer multiple of 2 pi for that matter. So we see, and I will change color, that I is just, and now we can also change the variables. We can say that x is phi. So we can also say x goes to phi and y goes to theta, just because they're angles and we would like to make that more clear by using the standard definitions or symbols that we use for angles. So I is integral 0 to 2 pi, 0 to pi sine of theta e to the square root 2 sine theta cosine phi, because remember we also did this, we set x plus pi over 4 to x, and x is phi, so we just get a cosine phi d theta d phi. Now, and this is the more astute observation out of everything else, if you ask me, is to realize that this entire thing here, sine theta d phi, is actually coming from an area measure, or dA factor. Because let me remind you what the in spherical coordinates, and spherical coordinates are sine theta cosine phi, y is r sine theta sine phi, and z is just r cosine theta. That's the convention I use. The dV, the volume factor, the measure for the volume, is given by r squared sine theta dr d theta d phi. And if we have to write the area for r, say for r equals 1, if we're considering the spherical shell at r equals 1, then the area factor, because that has a surface area factor, is just given by sine theta d theta d phi. And that's exactly what we have here. We have a sine theta, we have a d theta d phi, and the range is appropriate as well, because in these coordinates, phi goes from 0 to 2 pi, theta goes from 0 to pi. That's the entire range. Sorry, I used the same variable. That's the entire range we're working on. So it all agrees like that this factor sine theta d phi is just dA if we're integrating on the unit spherical shell. And we can also identify that the factor in the exponential is just square root 2 times x, because r is 1. Remember, r is 1. Again, we're on the spherical shell, r is 1. It's fixed to 1, so x is just sine theta cos phi, and that's exactly what we have, is square root 2 of x. So our integral is just integral over the unit spherical shell, which I will write like this: integral absolute value r equals 1 of e to the square root 2x, where x is defined as above, dA, and where dA is the surface area differential element. So all that is left for us to solve this problem actually is to find dA and basically, solve this surface area integral. How do we do that? Well, we have to go back to our multivariable calculus. And remember, when we had a nice sphere like that, we can use the method of revolution around an axis to find the area of it. So what we're going to do is we're going to take this circle and we're going to rotate it around the x-axis. What we're going to do is we're going to take a segment here. So let's say this is y of x. This is y. We have to write as a function of x. We're going to take that and we're going to rotate that around the x-axis. So that will trace out. I'm trying to be as neat as possible here. It will trace out this circle in the YZ plane, but we also have to stack them along the boundary, and the boundary term is a ds. So when we're taking the perimeter, so dA is combined of two things. So what we're doing is we're taking this radius y of x, that's the radius, and we're taking the circumference of those circles with radius y of x. So that will give us 2 pi y of x, because we're revolving around the x-axis to get a circle of diameter, or sorry, circumference 2 pi y of x in the yz axis, and then we're stacking them along the boundary ds. The boundary ds is just, the arc length ds. And the usual way of finding this arc length is the formula 1 plus dy over dx squared times dx. So we really need to find y of x, because we need it in two places. We need it here in the ds arc length element and the radius element here, y of x. I'm sorry I'm brushing over, this entire section fast. I'm assuming you've done some amount of multivariable calculus, because if you haven't, I might make a video on solids of revolution and finding this this surface area element. But for now, I'm going through it a little fast. So y of x, if we look at this this diagram, we know that this profile that we have here in the xy plane is of a unit circle. Because if we want to cover a unit spherical shell, we have to rotate. That's the solid of revolution generated by rotating around the x-axis, or even the y-axis. Here we're taking the x of the circular profile in the xy plane, a unit circular profile. So the equation for that is x squared plus y squared is 1. We can solve for y. We just need the top. We just need one radius. We don't care for the negative solution because it will be a square root. 1 minus x squared. We just care for the positive because y of x is treated like a radius that we're rotating to form a circle disk in the yz axis. So that is 1 minus x squared. And we can easily find ds, because dy over dx from this is minus x over square root 1 minus x squared. 1 plus dy over dx, the whole thing squared, that we need for the ds. That gives us 1 over square root 1 minus x squared. So in all, our dA factor is 2 pi y of x, which we already know is 1 minus square root 1 minus x squared. ds, which we've also found out, is 1 plus dy over dx squared, which we also know is 1 over square root 1 minus x squared, along with the dx factor. That cancels out nicely, and we're just left with 2 pi times dx. And that is nice because remember, in our original integral we had a dependency on the x, so it's nice to have dA, the surface area measure, in terms of x, because that makes integration easier. If we had a y on top, we'd have to revolve around this y-axis, so we'd have to take x as a function of y, and then the arc length parameter would have been dx over dy instead of dy over dx, like in here, like that. So it's all about perspective, and in the end it helps us really solve this, because now we have 2 pi integral minus 1 to 1, because when we're doing the solid of revolution, we're going across the entire profile we're varying the x is going from the entire profile on this circle. So x is going from -1 to 1. We don't need to worry about the, the negative y, because, we're rotating. That's where the 2 pi y comes from, because that's the entire circumference of that disk in the yz for a given y of x. But x needs to be varied because, that doesn't know. Whatever we had so far didn't know about this negative x part of the circle. And we have e to the square root 2 x dx, which is a very, very easy computation. We end up with square root 2 pi times e to the square root 2 minus e to the minus square root 2, which we can write in terms of some sinh, or I think it's a sinh. So we have, I think, 2 square root 2 pi sinh of square root 2. And that is pretty much the answer. We've solved the problem successfully. This was a nice question where we needed some knowledge of solids of revolution and surface area elements, and some nice trigonometric identities like this coming around to help us. I hope you liked this video. I'm sorry if I wasn't that clear with my, or as thorough as I usually am with my explanation of this solid of revolution to find the dA. I might make a video in the future. If you have any questions, leave them in the comment section. This is a very good problem for people who are especially in multivariable calculus, or are planning to use these, especially in engineering or introductory level physics, because many calculations in electricity and magnetism require this knowledge of, well, how do I manipulate, how do I find my surface area measure, how do I find my volume measure, how do I convert from spherical coordinates, Cartesian coordinates, connect them, and set up a double or triple integral. So that's it for this video, guys. Please like, share, and subscribe to my channel if you haven't already. Share my video to your friends. And in the meantime, stay home, stay safe, and keep doing math. Peace out.